Everybody. Uh, we're looking at section 6.2, uh, law of sines. This time we're looking at oblique triangles. And what that means is any triangle that is not a right triangle is an oblique triangle. The law of sines covers angle, side, angle, 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 side, and side, side angle, which is the ambiguous case. And we'll find out what that means. We're going to look at, we're not going to look at applications. This won't be on your notes. Okay, so what is an oblique triangle? First of all, solving a triangle means finding all of the angle measures and all of the side lengths. You could have a variety of pieces of information. The information must be enough so that you can find a unique triangle. An oblique triangle is any triangle that doesn't have a right angle. Some oblique triangles are acute, and what that means is every single angle is less than 90 degrees. An obtuse triangle means one of the angles is greater than 90. So in this little picture, angle C is greater than 90 degrees. We're going to use some abbreviations a lot going forward. So I wanted to have a nice slide for you to print out and remember. So you can be given the information as 3 sides. You can be given a side, an angle in between the side and another side. So see, the angle that you're given here is in between the sides that you're given. You can be given 2 sides and an angle where the angle is not between the 2 sides. You can be given an angle, a side, and an angle where the side that you're given is between the 2 angles. And you can be given 2 angles and a side where that side is not between the 2 angles. We're looking today at the law of sines. For the law of sines, and we'll see what that is in just a second, we're going to use law of sines to solve triangles when we know angle, angle, side, angle, side, angle. So anytime you know 2 angles, you're going to use the law of sines, whether the side that you know is in between or at the end. Or if you have side, side angle, 2 sides and an angle. Now, the law of sines states that the ratio of the length of a side of a triangle to the sine of that angle opposite is the same for all sides and angles in a triangle. Therefore, if triangle ABC is oblique with sides ABC opposite to angles ABC, then A divided by the sine of A equals B divided by the sine of B equals C divided by the sine of C. This is really, really handy and not too hard to use. In fact, it's quite easy to use. I do want you to put this information somewhere where you can access it easily. We said that the law of sines is for oblique triangles, but it's nice that it also works with the triangles we know. So let's consider a nice right triangle. Let's consider a 30, 60, 90 triangle. We know the proportions of the sides. We know that they are 1, 2, square root of 3. So if the short edge is 1, the longer leg will be square root of 3, and the hypotenuse will be 2. We know that already. Well, let's just look. If we have the sine of 90 degrees over 2, the sine of 60 degrees over square root of 3, the sine of 30 degrees over 1. Well, let's just simplify this. The sine of 90 degrees is 1. So we've got 1/2 in that first fraction. The sine of 60 degrees is the square root of 3 over 2. but we're dividing by the square root of 3, and those are going to divide out, and we're going to end up with 1/2. The sine of 30 degrees is 1/2. We're dividing by 1, so we get 1/2. Also, I bet you noticed that I flipped the law of sines in this example. The law of sines is very helpful in that when I'm looking for a side and I'm given an angle, I can put the side in the numerator. If I'm given a side and I'm looking for the angle, I can put the angle in the numerator. In other words, I can write the sine of A over little a equals the sine of B over little b equals the sine of C over little c. As long as all three of the ratios have sine in the numerator, then we're good to go. Let's look at an example. What if we are given that the measure of angle A is 42 degrees, the measure of angle B is 75 degrees, and C is 22 centimeters? Let's see. I'm just going to pretend like I don't know what the drawing is, and I'm going to draw A, B, C. Let's see. If angle A is at the lower left, then side A is opposite. Angle B is the lower right, so side C is opposite. Angle B is at the top, so side B is below it. Side C, we know that, and we know angles A and B. Oh, okay, we know an angle, side, angle. So this time, the side that we're given is in between the angles that we're given. You know 2 angles of a triangle, can you find the third? Always? Excellent. Yes, you know that the total measure of the angles in a triangle is 180 degrees. So if we subtract the measure of the other 2 angles, 42 and 75 degrees, from 180, we'll get the measure of angle C to be 63. Finding the lengths of A and B, then, we're looking for the length of A. So I'm going to put little a in the numerator. And I'm going to use little a over sine A equals C is what I was given, little c. So I'm going to put little c over sine C. I'm going to find A. So I'm going to multiply both sides of this by the sine of A. And now it's easy to write A equals C, side C, times the sine of A divided by the sine of C. And that's what I've done here. I've just written it in that form. And let's do that together. So I've got, first I'm going to make sure that radians are off. Yes, radians are off because I've got degrees here. And I'm multiplying 22 times the sine of 42 divided by the sine of 63, and I get 1.111. We're going to put everything to 2 decimal places for sides and 1 decimal place for angles, because why not? And I think I must have typed that in incorrectly because we didn't get the same amount. So let's do that again. 22 times the sine of 42 divided by the sine of 63. and we get 16.5216. And I'm just going to write 16.52, and we're in centimeters. Now, just like we solved the extremes of this first equation, a over sine 42 degrees equals c over sine c. We solved that for a, little a. We can also solve the inside part, b over sine b equals little c over sine c. We can solve that for b. So we're going to set, we've got b over the sine of b equals c over the sine of c. Notice again, we're looking for a side. So I'm going to put the law of sines with the sides in the numerator and the signs in the denominator. Again, I want to multiply both sides by the sine of b to get side b by itself. And we end up with side b equals little c times the sine of angle b divided by the sine of angle c. Let's do that. Little c is 22, and b is 75 degrees. And we're dividing by c, which is 63 degrees. And we get 23.8498. So I'm going to round this to 23.85 centimeters. So now we have solved this oblique triangle. It's oblique because there are no 90-degree angles. That's all that oblique means. And it is an acute oblique. I'm going to write that down. Acute, all the angles are less than 90. And it's oblique. No 90-degree angles. Great, let's do another. Let's solve the triangle. If we're given the measure of angle A is 30 degrees, the measure of B is 20 degrees, and the measure of side A is 45 meters. Well, again, I'm going to pretend that that drawing isn't there and draw any old triangle and label it A, B, C, any old way I want, where side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C. Now let's fill in what we know. The measure of angle A is 30 degrees. The measure of angle B is 20 degrees. And the length of side A is 45 meters. That means I've been given angle, angle, side. The side is not between the two angles. So we have angle, angle, side. Angle, angle, side. This time, again, we can figure out, oh, just one moment, please. I'm back. So anytime we know two angles in a triangle, any kind of triangle, we can find the third. We know that the total sum of all the angles in any triangle is 180 degrees. So we know that the measure of angles A plus B plus C equals 180. And we know A and B. The measure of angle A is 30, the measure of angle B is 20. So we know that A plus B is 50 degrees. And we could subtract 50 from both sides. And we get that the measure of angle C is 130 degrees. You can see that the sketch they provided is better than the sketch I provided. But the reason why I wanted to sketch that for you is so you could see it doesn't matter how you label the sides, as long as the sides are opposite the corresponding angle, you can tell whether you've been given angle, angle, side, or angle, side, angle. Now, this triangle is an oblique because there are no 90-degree angles, and it is obtuse because there's one angle with measure greater than 90. Angle C. All right, again, now we are looking for the sides. We have the measure of side A. We need to find the measure of sides B and C. And I'm going to orient the law of sines so that the sides are in the numerator. I've got little a over the sine of A equals, I'm going to first do angle B, equals B over the sine of B. I know everything in here except side B, except side B. So I'm going to multiply both sides by the sine of B to get little b by itself. Which is exactly what we have here. Little b is equal to sine of 20 times the measure of angle, the length of side A, which is 45, divided by the sine of angle A, which is 30 degrees. Let's see what that is. Let's see if I was right. So we've got 45 times the sine of 20 degrees divided by the sine of 30 degrees, and we get 30.7818, etc. And I'm going to call that 30.78, and it's in meters this time. And just like we did to find side B, we're going to do a similar thing to find side C. We're going to use little a over the sine of angle A equals little c over the sine of angle C. And we know everything in here except side C. I've got C over sine C equals A over sine A. I want to find side C, so I'm going to multiply both sides by the sine of C to get side C by itself. And we get that side C is equal to A times the sine of angle C divided by the sine of angle A. And let's see if I got it right. We have 45 times C was 130. And we're dividing by the sine of 30. And I get 68.94 meters. Now, unfortunately, we cannot check to see if the sides are correct with respect to one another using the Pythagorean theorem. That only works with right triangles. Okay, so now we've looked at both ways we can be given two angles. We could have a side in between them or a side not between them. However, there's a case where you can be given only one angle and two sides. And the angle that you're given isn't between the two sides. So we're given something like this. we have that's called the angles A, B, C. So the opposite angle A, I would have side A. Opposite angle B, I would have side B. Opposite angle C, I would have side C. So I could be given angle A, side C, and side A. 3 pieces of information. And notice that angle A isn't between the other angles, the other sides. This is called the ambiguous case because it's possible for us to be given 2 sides and an angle, and for that not to make a triangle. Let's look at how that can happen. What if we have, here's angle A, here's side C. What if side A isn't very long? And it's so short that it doesn't reach the base for angle A. Then there's no triangle. What if angle A is long enough so that it can actually swing in 2 positions? Here's side A, and it actually can swing into 2 positions, making 2 triangles. Then we would have 2 triangles with this information. We could have no triangles, or we could have 1. So let's see how we can find out how those things can happen. When you're given 2 sides and an angle not between them, then you need to find something called H. And let's see what that would be. So here we have ABC, and I've been given B and A and angle A. H is going to be the distance between angle C and side C if we drop a perpendicular. H, we can use sine to find out what H is. We know that the sine of A is H over B, opposite over hypotenuse, or that H is equal to B times the sine of A. The angle that we're given times the side not opposite that angle will give us H. H will tell us all we need to know. If angle A is acute, if it is less than 90 degrees, and side A is less than H, then there's no triangle. It's also no triangle if A is obtuse and A is less than B. Okay, there are 2 triangles if A is acute and H is less than A and A is less than B. So here, H is less than A, which is also less than B. In every other case, there's only 1 triangle. So let's play with that a little bit. Here we're given a side, A equals 15. We don't know units. B is 25, and the measure of angle A is 80 degrees. And you can see anytime the side and the angle are the same letter, then it's going to be side, side, angle, where that angle isn't between the 2 sides. So here we're given A is acute, A is less than 90 degrees. So A is acute. And to find H, it's called dropping a perpendicular. From C to AB. I see that H is going to be the sine of A times 25 times B. And let's see what that is. A is 80 degrees. Sine of 80 times 25 is 24.6. You see that side A is 15. It's much less. It doesn't even matter if it's much less. It is less than H. So we can write A is less than H. Therefore, there's no triangle. But what if we forgot to find H? What if we just went straight into the law of sines and we tried to find, well, the first thing that we'd be able to find, since we know side B is angle B. So let's see what happens. We're looking for the angle, so I'm going to put the sines in the numerator. We've got the sine of A over little a equals the sine of B over little b. I'm going to multiply both sides by little b to get the sine of B by itself. So B times the sine of A divided by little a is equal to the sine of B. All right. B is 50, let's see, B is 25. This A is 80, and little a is 15. Let's see it again. 25 times the sine of 80 divided by 15 equals, I get 1.6 approximately for the sine of B. Can sine of any angle ever be more than 1? That's right, it cannot. If we try to do inverse sine with this number, we get an error. Because the sine of a number can only be up to 1, never more than 1. The sine of B has to be between -1 and 1. So no triangle exists. If you get an error when you're solving for triangles, it could be it was the case where you were given two sides and an angle, and H was less than the opposite angle, opposite side. Let's look at another one in that same vein. We've got little a. I'm going to go ahead and draw just any old triangle. I've got little a is 6. Little b, I'm going to call this side B, is 7. Since little a is up and to the right, angle A will be down and to the left. Since little b is up and to the left, angle B will be down and to the right. And angle C has to be the opposite, or the only one left. Side C is opposite. So what are we given? Side, side, angle, side, side, angle, and the angle isn't between them. Okay, again, we're given angle A, and I'm going to drop a perpendicular. That will be H. H will equal the sine of the angle that is given times the side next to it. And what is that amount? Let's see. A this time is 30 degrees. Did it again? Okay, let's see. Sine of 30 times 7, we get 3.5. So H is 3.5. Let's get that information that we had. This time H is 3.5. A is 6. So A is bigger. So we're at least A is bigger than H. Is the remaining side that we were given larger than A? And it is. So in other words, if this had been, your side A was 7, is that right? No, side A is 6. H was 3.5. What if instead of 7, what if side B had been 5? Then there would only be one triangle. Even though H is less than A is greater than B. So it has to be in this order. A has to be less than, H has to be less than A, and A has to be less than B, both, in order to have two triangles. Great. I used this example because I found a picture that was kind of nice, but I really want to describe this picture. So when you just do the law of sines without any thought, you're going to end up with this triangle, the acute version of the triangle. That doesn't mean that all of the angles are going to be acute. It means that angle B is going to be acute. B is the angle opposite that side, that other side you were given. So you were given side A, angle A, and side B. So it's angle B that will be changing. Let's see. So let's use the law of sines. First, we want to find angle B. The sine of B divided by little b is equal to the sine of A divided by little a. I put signs in the numerator because we're looking for angle B. I'm going to multiply through by side B, and I get that the sine of capital B is sine of A over little a times B. Let's see what happens. A was 30 this time. B was 7, and little a was 6. So I get that the sine of B is 0.5833. I'm not going to round yet. So the sine of B is approximately 0.58. I can actually write it exactly by putting a bar. I'm going to use arc sine or inverse sine and make sure I'm in degree mode. I'm going to press second on my calculator anyway, and then inverse sine. And I get that angle B is 35.7. Let's call it 0.7. Now, remember that in the first two quadrants, sine is positive. Sine goes with y. In the first quadrant, x and y are positive. In the second quadrant, x becomes negative, but y is still positive. So, and remember, sine goes with y. That means there's an angle in quadrant 2 that has this same sign. And the way that we're going to find it is we're going to take this value and subtract it from 180. So we go 180 degrees minus 35.7. And I get 144.3. Let's just try it out. Let's see if the sine of 144.3 is the same as the sine of B. Not exact because we rounded, but I get 0.5835, 0.5833. So accounting for rounding, we get the same sign. So there are two angles that have the sign 0.5833, etc. One of them you get automatically on your calculator. The other one is 180 minus the one you're given. We're going to solve this using B acute, B sub A, and B obtuse, B sub O. So that we're clear, all of the other measures associated with B sub A will have an A subscript. And when I'm using B sub O, all of the other measures I'm trying to find will have an O subscript. I'll show you what I mean. Let's use B sub A. And I was using 2 decimal places when I did these notes. I would rather do 1 decimal place, but it really doesn't matter. So we've got 35.7 degrees. We can now find the measure of angle C, and I'm going to put this A here because it goes with B sub A. When I'm using this version of angle B, I get angle C is 114.32 degrees. Using that version of angle C, I can find little c sub A, which is 10.94 degree, measure whatever units these are. Then we use B obtuse, B sub O, and we find another angle C, and I'm going to call that one C sub O. And I get 5.68 degrees this time. And then small c sub O, because it goes with angle C sub O, is A times the sine of C sub O divided by the sine of 30 degrees, and we get 1.19. Let's solve a triangle given little a is 22, little b is 12, and the measure of angle A is 40. So we have and you can see side angle. The angle is not between the two sides, so we still have side angle, and that's the that's always considered the ambiguous case. Ambiguous. That means we're not sure. We have to find H in order to know what's going on. So this time, in order to find H, I've got H equals small b times the sine of A, and that will be 12 times the sine of 40. Let's see what that is. It's 7.7. Is 7.7 less than A? Is 7.7 less than little a? The answer is yes. So the only thing that, let's look at our conditions here. H is less than A. Is A less than B? Is A less than B? No. One triangle. One triangle. So you have to find H anytime you're given side angle. You need to compare H with the side opposite the angle given. And then you need to compare this two sides that were given. Let's go ahead and solve this problem. We've got the sine of B divided by little b is equal to the sine of A over little a. I'm putting the signs in the numerator because I'm looking for angle B. I'm going to multiply both sides by side B so that I have the sine of angle B is equal to little b times the sine of angle A divided by side A. Let's see what we get. Little b is 12. Angle A is 40. And little a is 22. And I get the sine of B is 0.3506, etc. I'm not going to round. I'm just going to do second inverse sine. And I get that B is approximately, angle B is approximately 20.5 degrees. The measure of angle B is approximately 20.5 degrees. For some reason, I did 2 decimal places when I did these notes, and I don't remember why. Now we know 2 sides. We know 2 angles. So I don't have to use anything besides the fact that the sum of the angles of a triangle, any triangle, is 180 degrees. So we have 180 minus the measure of angle A minus the measure of angle B, and that'll give us the measure of angle C. So let's see what that is. We've got 180 minus 40, that's A, minus 20.5, that's B, and we get 119.5, and so it'll be a little different here, 0.5 degrees. Now let's find side C. In order to find side C, we need to use the law of sines. This time I'm going to put sides in the numerator. I've got C divided by the sine of C equals A divided by the sine of A. I can multiply both sides of this by the sine of C. And on the left, everything cancels except for side C. On the right, I have little a times the sine of C divided by the sine of A. Let's see what we get. A is 22. C was 119.5. I wonder what I did wrong. Okay. So we have 22 times 119.5 divided by the sine of A. A was 40. So I get that side C has measured 27.78787, etc. And I'm going to call this 29.79. And whatever the units are. All right. What I want to do to end up this particular section is show you why this property, A divided by sine A equals B over sine B equals C over sine C, is true. So if we're given a triangle, any triangle, where we have the angles A, B, and C, and corresponding opposite sides, little a, little b, and little c, then the law of sines, let's look at this triangle. We have angle B, opposite side B. We have angle A, opposite side A. We have angle C, opposite side C. It really doesn't matter what orientation you have, whether angle A is lower left or B or C. But just using this particular orientation, let's find H. I know that this entire distance from B to C is A units long, but I wonder what this little piece of it is. I guess we'll have to find out. Regardless, I know that the sine angle B is equal to the opposite over adjacent over hypotenuse. Opposite over hypotenuse. So we could do that with respect to angle C. The sine of C is opposite over hypotenuse, because now we're looking at the triangle C, whatever letter this is, let's call it D, CDA. Now the hypotenuse is side B. So we get two things involving this opposite side. The sine of B is H over C, and the sine of C is H over B. Let's solve both of these equations for H. If I solve the first one for H, I've got to multiply both sides by C. If I solve the second one for H, I've got to multiply both sides by B. Let's do that right here. We get that H is equal to little c times the sine of B. And also, H is equal to little b times the sine of C. Well, H is H, right? H equals H. So I'm going to put that C times the sine of B is equal to side B times the sine of C, and divide both sides by the product sine B, sine C. I'm doing that to get signs in the denominator because the sides are in the numerator. Well, in the fraction on the left of the equals, the sine B's divide out. The fraction on the right of the equals, the sine C divide out. And what do we have? On the left, we have C divided by the sine of C. On the right, we have B divided by the sine of B. Isn't it amazing? Now, what we didn't do in this particular example was consider what would happen if the triangle that we were given, or actually the angle we were starting with, angle B, was obtuse. So now we are going to assume that. Oh, I see. We're going to assume that angle C is. So one of the original angles is going to be obtuse, greater than 90 degrees. So the H is actually not inside the triangle. H is opposite of the angle B. So my two triangles that I'm going to solve, I've got my two right triangles. I've got B, H is opposite, C is the hypotenuse, and I have another triangle. Almost true. This is almost C. I'm going to call this C prime. We have H and we have B for the hypotenuse. And I'm letting C prime be the acute angle that is complementary to C. Remember that C plus C prime is 180. Supplementary. Sorry. These two angles are supplementary. They add up to 180. All right. So we've got two angles whose sum is 180. The angle we were given was capital C. But if we have C prime instead, I know how to proceed. I know that if I use C prime, the law of sines is going to come out because that's what we had before. Can I? Can I? And the answer is yes. We know that C and C prime are also, well, if C is obtuse, greater than 90 degrees, then C prime will be less than 90 degrees, right? If it's in the triangle, it has to be one or the other. And C prime will be the reference angle. For angle C. Remember, if you have an angle in the second quadrant and you're trying to find the reference angle, you subtract that angle from 180. And C is definitely in the second quadrant because it's obtuse. So here's capital C. Here's C prime, but C prime is can also be drawn in the first quadrant. Well, remember that we had that one case where we had two triangles because there were two angles that had the same sign. Since everything in quadrant 2 has positive sign, every single angle, every single sign that you get in quadrant 1 will also be a sign in quadrant 2 because sign is positive in both quadrants. And remember the shape of sign? Here's quadrant 1. Here's quadrant 2. They all repeat. All values repeat. So the sign of capital C is the same as the sign of the reference angle C prime. And that's all we really needed. It's all written out here, so you can feel free to enjoy reading that. Also, I wanted you to see this symbol is one of the symbols that people often put at the end of proofs, QED. QED is an abbreviation for the Latin words quod erat demonstratum. And some people say that one translation of those words, what was wanted has been demonstrated. There are other ways to translate those words, but that's about it. And it means that the proof that you were requesting is completed. Great. Well, I hope y'all are doing well, and I'll see you again soon. Bye-bye.